Welcome back to the Explainers. So glad you're here. We are jumping right into the thick of it today, literally heading straight to the construction site. We've got a very specific, but honestly, absolutely crucial challenge to tackle: testing fresh concrete. Now, you might be sitting there thinking, okay, concrete is just concrete, right? Well, not exactly. The workability of that fresh mix literally determines the structural integrity of every single thing we build. And here's the thing. Sometimes the concrete we use for heavy-duty stuff, think massive highway pavements or huge foundational blocks, it's intentionally made incredibly stiff. So how on earth do we measure its workability accurately when it's basically solid? Let's get right into it. Okay, let's set up the core problem we're facing. In the construction world, the gold standard for testing how flowable or workable fresh concrete is something called a slump test. Basically, you fill a cone, pull it straight up, and watch how much the concrete, well, slumps or falls down. But here's the catch, and it's a big one. What do you do when your mix has very, very low workability? We're talking about concrete that's so stiff it barely even moves. A standard slump test completely falls apart here. Why? Because the concrete won't slump at all. It'll just sit there like a rock or maybe just crumble into pieces. We obviously need a totally different tool for this job. And that right there brings us to the star of today's explainer. When a mix is just way too stiff to slump, engineers turn to a highly precise standard. It's known as the compaction factor test. Specifically, it's defined under the Indian standard IS 5515-1983. Now, I want to be clear, this isn't just some makeshift workaround. Not at all. This is a rigorously designed, fully standardized engineering solution built for this exact scenario: concrete mixes with incredibly low workability. It completely removes the guesswork and gives us the hard, quantifiable data we actually need. So what does this apparatus actually look like? Well, honestly, it kind of looks like a giant baking sifter on steroids, doesn't it? But every single piece has a very specific job. Starting right at the top, you've got the upper hopper. Right underneath that is a hinged trapdoor. Then below that one, there's a slightly smaller lower hopper, which, you guessed it, has its own trapdoor at the bottom. And finally, sitting flat at the base of the whole stand is a simple heavy-duty cylinder. Keep this setup in your mind's eye because we're about to use this exact tower to put our fresh concrete through a little physical obstacle course. All right, let's run through that obstacle course right now. Step 1, we take our fresh, super stiff concrete and gently fill that top hopper. But here's the absolute golden rule. No compacting allowed. No pushing, no vibrating, just let it sit. Step 2, we swing open that top trap door and let gravity take the wheel. The concrete drops right down into the lower hopper. Step 3, we immediately snap open the lower trap door, letting the concrete free fall one last time straight into the cylinder at the bottom. Step 4, we carefully strike off, or basically scrape away, any excess concrete mounding over the top rim. And finally, Step 5, we take that perfectly flush cylinder and weigh the concrete inside. Now this number, this is absolutely crucial. We call this the weight of the partially compacted concrete, simply because the only force packing it down was gravity pulling it through those hoppers. Okay, but to make our final calculation work, we need a baseline to compare that first weight against. So enter the reset phase. We take that cylinder and empty it completely. Now we're going to refill it with the exact same batch of concrete, but this time we do it in distinct layers. And instead of letting gravity do the work, we're forcing it. We compact it completely. The standard actually requires us to use heavy vibration or aggressive manual tamping. We want zero air pockets in there. Once that cylinder is packed to its absolute maximum capacity, we weigh it again. Boom. Now we have our second crucial variable, the weight of the fully compacted concrete. This right here perfectly captures the elegance of this entire test. To find the actual compaction factor, it's just a simple formula. You take the weight of the partially compacted concrete, remember, that's the first weight where we just let gravity do its thing, and you divide it by the weight of the fully compacted concrete, our second weight where we used maximum physical force. What this math does is spit out a clean, simple ratio. It tells us exactly how well this super stiff concrete can compact itself under its own falling weight, compared to its maximum possible density. It's just a brilliant, purely mathematical way to pin down workability. So what do these ratios actually look like in the real world? If we compare standard slump measurements to our new compaction factor ratios, you can really see a clear trend. For an incredibly stiff mix, the kind that would barely give you a tiny slump of, say, 0 to 25 millimeters, the compaction factor comes out to roughly 0.78. But as the concrete gets more workable, like a 50 to 100 millimeter slump, the compaction factor goes up to 0.92. And for a really flowable slump of 100 to 150 millimeters, the factor jumps all the way to 0.95. Essentially, here's the rule of thumb. The closer that number gets to 1.0, the easier the concrete flows and compacts all on its own. But if there is one single thing you take away from this entire explainer, it all comes down to this specific number, 0.7. Engineering standards do not mess around with us. A compaction factor of less than 0.7 is absolutely 100% not suitable for use, period. Think about it. If your partially compacted mix weighs less than 70% of your fully compacted mix, it means it's just too dry, too stiff, and completely structurally unviable. It is a vital safety threshold baked right into the IS 5015 standard to make sure our bridges and buildings actually stay standing. It really makes you wonder, doesn't it? The next time you walk past a massive construction site, just think about how many invisible, mathematically precise tests are quite literally holding up the ground beneath your feet. Thanks so much for joining me for this explainer. Keep asking those great questions, and I'll catch you in the next one.